Is it just me, or do you think we need more creative coding tutorials on YouTube? There are a lot of videos teaching you the basics of programming, but how are we supposed to learn some of the more interesting effects? That's why I created this series, where we combine basic, fundamental JavaScript techniques into creative coding experiments, generative art, animations for websites, and more. For science, of course. In today's JavaScript project tutorial for beginners, I will show you something new. We will create simple particle system on HTML canvas element, and we will give particles some basic physics. I will show you how to simulate wind and gravity forces. Then we will learn how to make particles bounce, and we will set up collision detection with a regular website element. For example, H1 title element, but it will work with any HTML element you choose, even with multiple ones. If you want to have particles that react to your website menu and articles, for example. At the end of this tutorial, you will be able to create a background for your website with particles that respond to any HTML element of your choice. I have already tried to do something similar once before, but this time I have an improved, very simple, reusable solution. I will also show you how to create different skins for this effect, using, for example, liquid filter or constellations effect. Let's learn JavaScript together. Join me for another particle systems experiment. Hi coders, welcome to my JavaScript laboratory, where we use HTML, CSS and JavaScript to create all different kinds of interactive animated effects. That includes games, generative art, web design elements, and much more. In each tutorial, I take you step by step through the codebase as we build our project completely from scratch. And that's not all. We don't use any libraries or frameworks, so not only we build cool stuff, but in the process we also learn fundamental JavaScript techniques. These techniques are completely transferable to other kinds of front-end web development projects and will help you to pass your coding interview and get your first programming job. Learning how to code is a big journey some of us take, and my goal is to try and keep you motivated by showing you all different kinds of cool things you can build with JavaScript, if you decide to commit and stick with it for a while. I am here to help you to achieve your goals. If you want to make me happy, you can click the like button. You can also leave a comment, even just to say hi. It doesn't have to be a long message or a question. It would be nice to know who's watching. Let's build some generative art today. You ready? Then get some coffee and fire up your VS Code. Let's go. In index.html, I link style CSS and script.js files and create HTML5 canvas element with an ID of canvas1. In style CSS, I do basic style reset to make sure everything appears the same across all different browsers. I use asterisk selector to target all elements on the page and set margin to 0, padding to 0, and box sizing to border box. This means elements border and padding will be included in its total width and height. I give canvas position absolute, background blue just so we can see it for now, top 0, left 0, width 100%, height 100%. Next, I will target ID title1. Actually, I haven't created this element, so back in index.html, I create a h1 element with an ID of title1. And I give it text that says, for example, JavaScript. Back in style CSS, I give title position absolute, top 50%, left 50%, transform translate -50% will center the text both vertically and horizontally in the middle of the page. I change font size to 120 pixels, line height to 110 pixels, I zoom out a bit in the browser so you can see the page better. Border 1 pixel solid black, just so we can see what's going on for now. I can remove the blue background from canvas on line 8, and on line 21, let's make the border thicker. If I change the text, I can see it's aligned. I set border top to 5 pixels solid black. I create a before pseudo element. This is a special type of element that doesn't exist in HTML markup and is entirely created with CSS. It has one mandatory property called content. We can leave it empty or put some text in here. I put down, for example, is awesome, because JavaScript is awesome, isn't it? You can see it puts the text before the actual title text like this. I want to move it around, so I give it position absolute, bottom minus 70 pixels, font size 40 pixels, text align center, and width 100%. In script.js, I create a variable called canvas, and I set it equal to document.getElementById. I gave my canvas ID of canvas1, so I pass canvas1 here as an argument. Now we have a reference to HTML canvas element saved in a JavaScript variable called canvas. Now I need to let JavaScript know if I want to be using 2D or 3D methods. So I create another variable called ctx, shortcut for context, and I set it equal to canvas.getContext, and I pass it 2D as an argument. You can see that this canvas is referring to canvas variable from line 1, and I'm passing it 2D as an argument. This makes this method return something called canvas rendering context 2D, which simply is just an object that comes built in every modern browser. And this object contains all 2D canvas drawing methods. If I wanted to do 3D, I would just pass it word WebGL instead of 2D here on line 2. If I console log ctx, you can see that it now holds canvas rendering context 2D object. And if I open that object, I can see all of its properties like filter, font, line width, stroke style, and so on. All of these can be assigned a different value to create different unique effects. Down here on the object's prototype, I can also see all built-in 2D canvas methods that are available for us. Some of them we will use today, like arc method to draw circles or fill style to set color of these circles. I will cover the other ones in later videos of the series to show you many awesome effects you can create with this. I can remove the console log, and now, as I said, our custom ctx variable contains a reference to this built-in canvas rendering context to the object. So if I want to call any of the methods we just saw, I call them like this. For example, ctx.line2. They say everything in JavaScript is an object, and you can certainly see that here, where the entire Canvas 2D API is just a set of properties and methods on an object. Let's continue with our effect. I set canvas width to window in width and canvas height to window in height. I create a let variable called particles array, and I set it equal to an empty array, like this, by using empty square brackets. I use let variable here because later on I want to empty this array. I will just say particles array equals empty array square brackets. If I used const variable here instead, I wouldn't be able to do that because value of const variable cannot be reassigned. I would still be able to change individual elements in the array, but I would not be able to reassign it to a completely new empty array. That's why I use let here, you will see later. I create a JavaScript class, which is one of few techniques we can use when we want to create many similar objects. In this case, I want to create many objects. Each one will contain data for one particle, such as its current x and y coordinates, its color and size. We will then be updating this data to move particles around and pulling this data out to tell Canvas where exactly to draw the particle for each frame of animation. Let me show you and explain everything step by step now. Each class has one mandatory method. A method is simply just a function attached to an object. This mandatory method on JavaScript ES6 class is called a constructor, which runs only once per each object. In our case, once per each particle, at the point where we initialize the class by calling it using the new keyword. The new keyword is a special command in JavaScript, and it will call particle class and its associated constructor method. Constructor's only job is to create one new blank object and assign it values and properties based on the blueprint inside the constructor. So let's write that blueprint now. Each constructor will expect two arguments, x and y. These will be the initial x and y coordinates where the particle first appears on canvas before it starts moving. They will be calculated outside, as I will show you in a minute, so I have to pass them as arguments like this. Now I say this.x is equal to x. It's a bit weird syntax, but also very simple. All I'm saying here in the blueprint is telling the constructor x property on this new blank particle object you are creating will be equal to x variable that was passed as an argument on line 8. That's all. I do the same thing for this.y vertical coordinate. We will also have other properties on each particle, such as this.size, which will determine how big each particle circle is. Since this value will be randomized internally here inside the constructor blueprint, I do not have to pass it as an argument on line 8, because it is not coming from the outside. Size property on each particle will be created and randomized here inside the constructor on line 11. At first, I will make all the particles the same size, let's say 10. But if I call math.random times 10 here, for example, each particle created by this constructor will have a random size between 0 and 10. We will do just that, but a little bit later. This.weight will determine how heavy the particles are, and this will affect how fast they fall and also how high they bounce when they collide with something. I will set it initially to 2, but we could also randomize this value so each particle behaves a bit differently. This direction x will be force pushing on particles along horizontal x-axis, so if I set it to 1, particles will be pushed slightly to the right. You will see it in a minute when we draw our first particle. I will show you what all of these values do. Let's take it step by step to make sure we understand what's going on. So, this is our blueprint. Whenever we call new particle, JavaScript will invoke class constructor on line 8, create one new blank object, and give it values and properties based on the blueprint we just declared between lines 9 and 13. Each particle will also have access to custom method I call, for example, update. The job of this method will be to calculate and update particle's position for every frame of animation. Each particle has a weight property, as we declared in constructor blueprint on line 12. I want particles to get heavier the longer they fall, which will create interesting movement trail, especially if they are being pushed to the side by wind at the same time. This is also important when you want to make particles bounce. I will show you how exactly it works in a minute. So here I say for every frame of animation, increase particles' weight by a very small amount. The longer they fall, the heavier they get. At the same time, I want particles to move down, so I have to update their vertical y coordinate. For every frame of animation, increase particles' vertical y position by particles' weight. If particles' weight is 1, for example, it will move 1 pixel down for every animation loop. We will create animation loop in a minute. So here particles are getting heavier and their weight is being added to their vertical y position. Each particle will also need a custom draw method. The job of this method is to take values like position x and position y and size and draw a circle there representing our particle. Here I will be using all built-in Canvas 2D API methods we invoked on line 2, if you remember, by calling canvas.getContext2D and saving it as a reference in a variable I called ctx. That's why all Canvas 2D methods are now available on my ctx variable, and I can call them like this. ctx fill style determines fill color of canvas drawings. I will set it to red. Don't forget to put the color in quotes. When you draw a circle on canvas, it's different than drawing a rectangle. Rectangle is a shape, but circle on canvas is considered a path, similar to when you draw a line. So to draw a circle, first I need to call begin path, which will tell JavaScript we want to start drawing. Now I can call built-in canvas arc method, which takes at least 5 arguments. We need to pass it all these arguments so that JavaScript knows where we want to draw our shape. It expects position on the horizontal x-axis, so I pass it this.x from line 9. Position on vertical y-axis will come from our blueprint as well, from this.y on line 10. Now we need to give it radius, which will determine how big our particle is. I pass it this.size from line 10. We are drawing a circular path, so now we need to tell JavaScript where along a circular path area we want to start our circle shape. At what angle? I will start at angle 0, so I pass it 0 as start angle argument, and as end angle I pass it math.pi times 2, which is a value in radians that converts exactly into 360 degrees. And some of you might know that 360 degrees is a full circle. If we pass a different start angle and end angle values, we can draw a half circle shape or many other shapes here as well. But today we want our particles to have a shape of a full circle. When I'm done drawing, I call close path and I call built-in fill method to fill our circular path with red color. I need to call all of these methods from our custom ctx variable. So this is our particle class, which we can now call anytime using the new keyword, and it will create one new blank particle object and assign it properties and values as declared in particle class constructor between lines 8 and 13. Every particle object we create this way will also have access to update method, which will calculate particle movement for each frame of animation. And each particle will also have access to draw method, which will take information like updated position and size, and it will draw a circle there, representing our particle. Now that we have our class, we can try and create the first particle. I create a constant variable, I call for example particle1, and I set it equal to new particle. The new keyword is a special command in JavaScript, and it will make JavaScript jump up to line 8 and call JavaScript class constructor, create one new blank object, and assign it values and properties as declared between lines 9 and 13. On line 8, you can see our particle class constructor expects two arguments, x and y, which will determine position on x and y axis where the particle appears when it's first created, before it starts moving, falling down in our case. So here I pass it 100 as x coordinate and 10 as y coordinate. The last thing we need is a for loop that will draw our canvas over and over again. I create a custom function I call for example animate. Its job will be to call everything that needs to run for every animation frame. It will be calling it over and over, creating our animation loop. Let me show you. For every frame of animation, I want to take particle 1 we just created on line 27, and since it was created using our particle class, it has access to all associated class methods declared on that class, in this case update and draw. So for every frame of animation, I call update from line 15, which will make particle heavier and it will animate it down along vertical y-axis as declared on line 17. I will also call custom draw method from line 19, which will take these updated x and y coordinates from particle object, and it will draw a circle there representing our particle. I can create set interval, for example, to run this animate function over and over, but there is much better way to create animation loop by using built-in request animation frame method. This method is very simple. It just runs once and does one thing. It simply just calls function we pass it as an argument. It calls it just once and then it stops. So here I say request animation frame and I pass it animate, the name of its parent function from line 29. This will cause animate to run all its code on lines 30 and 31, and when it reaches line 32, it will just call itself again, creating our animation loop through a programming principle called recursion. Request animation frame is optimized and it will adjust frame rate to your screen refresh rate, so it's recommended to use over set interval. We have just declared animate. All I have to do now is to call it by saying animate and brackets like this. This will kick off our animation loop. Yes, so we have a particle falling down. It leaves a very long trail because we are not clearing canvas from old paint. We can either clear all of the old paint, so we will just see one red circle moving around, but for this effect I want particles to leave fading trails behind. So instead of clearing the entire canvas from old paint after every animation frame, I will just use a semi-transparent rectangle that will be overlaying the canvas over and over. This will create an illusion of slowly disappearing paint, as the semi-transparent rectangle layers itself over and over on top of the old canvas paint. To do that, I just set fill style to RGBA 255 255 255, which is white color, and the last attribute is for alpha. Opacity, it will be 0.0.1, very low opacity. With the fill style declared, I use built-in fill rectangle method, and I want this rectangle to be the exact same size of our entire canvas, covering the canvas with semi-transparent rectangle over and over for every animation loop. You see, it makes the trail slowly fade away. Click the like button please if you're getting any value from my tutorials. Now back to the video. On line 27, I can change value for x and y to make particle appear at different coordinates. We have a problem. When the particle falls down, it never comes back again. To fix that, here on line 16, inside update method, I create an if statement. It will check if this.y is more than canvas height, which means if particle has fallen past the bottom edge of canvas. If it did, I just set its vertical y coordinate to 0 minus this dot size, which will hide the particle just behind the top edge of canvas. You can see it resets now. You might also notice it's falling faster and faster because here on line 17 we say for every frame increase its weight by a small amount. This will add up over time and make the particle fall very fast. Too fast actually. To fix that, here inside if statement, every time particle falls below the bottom edge of canvas, reset its weight back to the original value, which was 2. Another thing you might notice is that particle follows the same path over and over. I would like it to fall from random point every time it falls off screen. So I set its horizontal x coordinate to a random number between 0 and canvas width. Now the particle falls from random points all over the canvas. Great. On line 13, I declared a variable I call direction x and I set it equal to 1. This will simulate wind that pushes on particles horizontally. It will push on them at the same time as they are being pulled down by a weight variable, which represents gravity. So we will have both wind and gravity forces affecting particle movement. On line 23, inside update method, I say for every frame of animation, add particle's direction x property to its horizontal x position. Let's make direction x a negative number on line 13, so particles get pushed to the left. You can see we get slightly curved path because we have wind coming from the left and gravity pulling down. And because particle is getting heavier the longer it falls, as specified on line 21, gravity is becoming stronger than wind over time, giving us a curved movement path. If I change this dot weight on line 12, it will make particles fall faster. On line 21, I can also change how fast particles' weight increases for every animation step. On line 33, we created particle 1. Let's go ahead and create one more. I will call it particle 2. I use new keyword again to invoke another instance of our particle class, which we'll call class constructor, create one new blank object, and I can pass it different starting coordinates by giving it arguments for x and y, for example 100 and 100. The other properties on this particle 2, like size and weight, will be assigned based on the rules we specified inside constructor earlier. On lines 40 and 41, I am calling draw and update methods for particle 1. I also need to call these methods for particle 2, like this. On line 34, I make sure I name it particle 2, and now we have two falling particles, both created by the same class constructor, and both have access to shared update and draw class methods. So this is how you use JavaScript ES6 classes to create many similar objects. As you can see, our particles are similar, they have the same set of properties and can access the same methods, but some of these properties can have different values. For example, each particle has different x and y coordinates. It can also have different size and color, but overall they are similar in structure and behavior. This is what they mean when they say use JavaScript classes to create many similar objects. Let's take it to the next level. What if I want to create 300 particles using JavaScript class? I could create each particle one by one, like we did create particle 1 and particle 2 on lines 33 and 34. And then I would have to call update and draw for each of them individually, like we did between lines 40 and 43. But that would be a lot of repetition. That's not a very good way to do things. Lucky for us, JavaScript has loops, and we can use a power of for loop to declare all of this once and tell the for loop to repeat it 300 times to create 300 particles. Up here on line 6, I create a variable I call number of particles and I set it equal to 300. On line 22, I adjust weight to make particles fall a bit slower. On line 34, I create a new custom function called init. Its job will be to run a for loop and fill particle array we declared on line 5 with 300 randomized particles using our particle class constructor. Inside init, I create a for loop. This will run 300 times because I set the number of particles to 300. I can delete particle 1 and particle 2 because we will create many more now. I want all new particle objects to be stored in particle array we declared on line 5. So here inside for loop that will run 300 times. Each time it runs, I target particles array and call built-in array push method. This method just takes whatever we pass to it in brackets and pushes it at the end of array we call it on, in this case particles array. So I pass it new particle, which, as we explained, will call particle class constructor and create one new blank object and give it properties and values based on constructor blueprint we wrote earlier. In our case, these properties are size, weight, and so on. We also know our particle class constructor expects two arguments for x and y. I can just pass some number here, but that would mean all particles appear at the same point, in the same location coordinates. I would prefer if each particle appeared at randomized position all around the canvas, so I create a temporary variable I call x. Its only job is to create a random number, so I can pass it as x coordinate to class constructor on line 37. I say const x is equal to random number between 0 and canvas width. I do the same for vertical y coordinate. Y is a random number between 0 and canvas height. So these two x and y variables will just randomize coordinates for each particle, and we pass them to new particle on line 38. That's it really. Since this for loop runs 300 times, it will create 300 randomized particles for us. I can console log particles array to see if it worked. To run custom init function and to fill particles array with 300 randomized particles, I need to call init like this, init brackets. I open Google Chrome console and I can check if we are console logging particles array correctly. I can see we have an error here on line 49. That is because I'm trying to call update and draw on particle 1 and particle 2, but these objects don't exist anymore. I deleted them. So I delete this code as well. And I can see particles array in console, and it contains 300 particle objects. Perfect. Now all I have to do is create a for loop that will cycle through these 300 particles one by one, and it will call their associated update and draw methods. Inside animation loop on line 47, I create a for loop. It will run as many times as many particles we have in particles array, as long as I is less than particles array length. Inside, I refer to each individual particle in that array using I, which stands for index. So particles array square brackets I. I is taken from the for loop, so it's 0, then 1, then 2, all the way to 300. So particles array I is the first, second, third element in the array and so on as the for loop runs, and I variable on line 47 increases up to 300. For each particle in the array, I call its update method to apply forces and calculate its new x and y position. Then I call draw to take these values and draw a circle there. Here we go. We are using JavaScript class to create 300 animated particles, and we are applying gravity and wind on them. On line 20, inside update method, we have an if statement that checks if particle has fallen off screen, and if it has, it resets it. I want to reset its horizontal x position a little bit more to the right, so we don't have the big empty area in the bottom right corner here. I say reset its x position to be a random number between 0 and canvas width times 1.2. 1.3 maybe. It will spread particle circles slightly to the right. All particles are the same size. On line 12, I can set this dot size to a random number between 1 and 16. That looks a bit more interesting. On line 13, we give each particle base weight of 2. On line 22, we increase this weight value slightly the longer the particle falls. And on line 23, we add this ever-increasing weight to particle's horizontal y position, which simulates gravity force. Let's make particles fall at different speeds by randomizing this dot weight on line 13. I can, for example, set it to a random number between 1 and 2. That's very subtle. How about a random number between 1 and 6? Interesting. Let's do a random number between 1 and 2 for now. On line 27, I change fill style to orange-red. Or maybe green. How about purple? I forgot about one thing. We are resetting weight whenever particle falls off screen. So to keep our randomized weight values, I also have to add math.random here on line 19. Now we can see some particles fall slightly faster than others. It will also affect how high particles bounce when we set up collision detection with text field, as I showed off in the beginning of the video. If I change value here on line 22, wind might be stronger than gravity and particles start moving more horizontally. In index.html on line 11, we created h1 title element with text that says JavaScript. Let's make particles bounce when they collide with that text. I covered everything slowly step by step so far. I will also explain everything I do now, but we are moving into a slightly more advanced territory. So if you are a complete JavaScript beginner, maybe watch this next part twice to make sure you understand what's happening, if you want, of course. First, I will target element with an ID of title1 by getElementById, and I save it in a variable I call titleElement. I create another variable called titleMeasurements, and here we will use special built-in JavaScript method called getBoundingClientRectangle. It returns an object that contains the size of an element and its position relative to the viewport, relative to the browser window. That object is now being held in our custom titleMeasurements variable, so if I console log it, I can see we have all details about title element, such as bottom position, height, left position, and so on. Perfect. If I go to style CSS and I change these values, for example distance from top, now if I go back to browser and refresh the page to run the measurements again, I can see it updated top position on our object. Back in script.js on line 11, I can delete the console log and I create a custom variable I call, for example, title. I set it equal to a JavaScript object. To run collision detection between particles and this title element, I will need its x and y coordinates. I will also need its width and height. I get all of these values from titleMeasurements variable. Position on the horizontal x-axis will be its left property, distance from the left edge. Vertical y position will be its top property. Width is equal to titleMeasurements width, and height is titleMeasurements height. So now we have successfully converted HTML elements bounding box into a JavaScript object. We can use these values from that object to draw that bounding box on canvas. Inside animate function on line 62, I call built-in canvas fill rectangle method, which takes 4 arguments and draws a rectangle. It expects x coordinate, so that will be title.x. Y coordinate is title.y. Same goes for width and height. And if I refresh, I can see we are drawing a rectangle on canvas that matches bounding box of HTML h1 title element. I will use this as a reference to calculate collision detection between this rectangle and every individual particle. One thing I will adjust is the height, because I don't want particles to bounce off from this right edge. So I will reduce height to, let's say, 10 pixels. On line 61, I can delete the rectangle that represents collision detection area for title element. I still have its values stored in custom title object, so I will use these values to check if particles and title are colliding. Inside update method on line 36, I will check for collision between each particle and title element. I create an if statement and use common collision detection formula between two rectangles. Let's pretend particles are not circles but rectangles today. It will work and it will look good. It's also much easier to calculate. To check if title and particle are colliding, I need to check 4 things. This might be a bit complicated if you are a complete beginner, but don't worry. It will make more sense to you if you use it more than once. We are entering advanced territory, so don't feel bad if you get a bit lost here. I will try to help you understand as much as I can. In the first of our 4 collision detection checks, I need to see if this particle's x is less than title x plus title width. The second thing I check is if particles x plus particles size is less than title x. These 2 checks combined determine whether or not particle and title intersect on horizontal x-axis. We are checking if particle is on the same x position as title, just horizontally now. It could still be below or above the title, so we don't know if they intersect just yet. To be sure, we also need to check if particle and title collide vertically, so I do the same thing for vertical y-axis. I check if this particle's y is less than title y plus title height, which means, in other words, is the particle higher than bottom edge of title rectangle? At the same time, I also check if particles y position plus this particle size is more than title y, or in other words, is particles y position below title's top edge. Notice that for all of these 4 statements I use double ampersand, so it means all of these conditions need to be true for collision to be true. On line 38, I check if particle's horizontal x position is less than title's right edge. On line 39, I check if particle's horizontal x position is more than title's left edge. On line 40, I check if particle's vertical position is less than title's bottom edge. And finally, on line 41, I check if particle's current vertical y position is more than title's top edge. If all of these are true, we know that particle is colliding with title element. We will enter if statement, and here I want to make particle move just 3 pixels up in minus direction on vertical y-axis if it hits title element. You can see that particles slide a bit to the left, but eventually they fall through the title. That is because on line 32 I am increasing weight over and over, and on line 33 I am adding that ever increasing weight to particle's horizontal y position. Eventually, weight will be so much so it will just push particles through. If I want particles to bounce when they collide with the title, all I have to do is to multiply this dot weight times minus 0.5. What that does is, let's say particle's current weight is 6 when it collides with title. By multiplying its weight times minus 0.5, it will convert it from plus 6 to minus 3, making the particle bounce and move in the opposite direction. At the same time, that minus 3 value is still being affected by line 32, where we are adding plus 0.0.1 to particle's weight, so eventually it will go back to 0 and it will start increasing into positive numbers. Because particle's current weight is constantly being added to particle's vertical position on line 33, this will cause particle to bounce up, then slow down when its weight reaches 0, and start falling down again as its weight property grows into positive numbers again because of line 32. You can change how high the particles bounce by changing value here on line 44. Now you know how bouncing movement works on canvas. If you are a beginner and you managed to code along to this point, well done. This is not beginner stuff anymore. Great job. Up on line 6, I can change number of particles to, let's say, 1000. We have a small problem that comes with any HTML canvas project. When you stretch or resize browser window, the entire canvas drawing stretches like this. You can also see that it distorts the collision detection area and particles now don't bounce from the correct positions. To prevent this from happening, there's an easy fix. I create an event listener. JavaScript event listener expects 2 arguments: type of event to listen for and callback function to run whenever that particular event occurs. We will be listening for a window resize event, and when user resizes browser window, I will run the following code. We will measure the canvas again and set canvas width to window in width and canvas height to window in height. I will also call our custom init function we declared on line 55. I adjust it a little bit by making sure particles array is always empty before this function runs. So now, whenever window resize event occurs, our custom init function will delete all particles from particles array. It will run a for loop again and create completely new set of randomized particles depending on new canvas width and height dimensions. Well done, resizing the window doesn't stretch our drawing anymore, but we can see that title collision area still gets distorted. That's also easy to fix. I take title measurement variable. Notice that I am not using a variable keyword, just variable name, which means I am taking the same variable and reassigning it different values. If I used var, let or const here, I would be declaring a new variable. We don't want that. So I reassign our existing title measurements variable by selecting title element variable that holds reference to title HTML element, and I'm calling get bounding rectangle again. This will just measure position of title element relative to browser window again, after we resize the window. Now I take title object we declared on line 11. Notice I also don't use var, const or let here, so I'm not creating a new variable, just updating existing one. I can actually go up here on line 11 and just copy all these values like this. Now, every time we resize window, we recalculate canvas width and height on lines 78 and 79. We measure title element again on line 80. We take these values from line 80 and update existing title object from line 11 here on lines 82 and 85. And lastly, we run init function, which will delete all current particles and create a set of completely new ones and spread them randomly around the new resized canvas area. All fixed. Okay, challenge time. The first one is for the beginners. Are you able to change the direction from which the wind is blowing? To do that, you would have to change value on direction X property. If you're more advanced, are you able to change color of particles to look like this? I covered how to work with canvas gradients in my previous video. If you want to learn more, I will leave a link in the video description. Thank you very much for watching. Don't forget to click the like if you like my stuff and want me to make more. Subscribe and hit the bell icon to get notification when I release another creative coding tutorial. While you're here, you can also check out some of my other creative coding tutorials. See you next time.